There are two types of numbers in the mathosphere that we deal with, and these are real numbers and imaginary numbers. Imaginary numbers deal with the square root of -1, and we don't really deal with that until about the algebra 2 level. But with real numbers, we can look at the types of real numbers and classify the numbers as either rational numbers or as irrational numbers. All right. And the key phrase that we hone in on with the words rational and irrational is the word ratio, or the prefix ratio. So we see ratio, rational and irrational. So the difference between a rational and an irrational number is that rational numbers can be created by finding the ratio of two integers. All right. So the ratio of two integers, for example, is like a fraction. So I can create the rational number 0.5 by creating a ratio between the two numbers 1 and 2, right? So 1 over 2 is the same as saying 1 divided by 2. This is the ratio of 1 to 2. That gives me the rational number 0.5. In contrast, an irrational number cannot be found as the ratio of two numbers. So basically, you cannot create a fraction that is equivalent to an irrational number. You can always create a fraction that is equivalent to a rational number. An example of an irrational number is something like the non-perfect square root. So for example, if I have the square root of 2, the square root of 2 is asking the question, what number times itself is equal to 2? And there is no integer, there's no whole number that you can multiply by itself that will give you 2. So the square root of 2, we can approximate that as the number 1.414. If you put it in your calculator, you get 1.414213562. So your calculator will approximate it to a certain number of digits, but ultimately it is considered a non-repeating, non-terminating decimal. The non-repeating means there is no pattern in the decimal. These numbers are random. There's no pattern here. And non-terminating is what the ellipses here, the dots, means that it does not end. So non-terminating, the decimal goes on forever into infinity. And non-repeating means there's no pattern. Another example of an irrational number in geometry we deal with, and that is the ratio of a circle's circumference to its perimeter, which we can approximate by the decimal 3.141592, 654, and so on. Again, the ellipses here means that it is non-terminating, means that this decimal continues to go on and on and on. Our calculators usually only approximate it to a certain number of digits, and there is no pattern. These are irrational numbers, right? There are no two integers that you can divide to give you this number. Right? There are no two integers that you can divide to give you this number. There are no two integers that you can divide to give you this square root of 2 or the square root of 3, right? And so forth. Therefore, we can only approximate these numbers as decimals. So the square root of 3 is about 1.732, blah, 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 and it goes on forever. These are irrational numbers. We cannot create these numbers as the ratio of two integers by dividing two integers. And in contrast, rational numbers, we can. So rational numbers, we can further divide them into groups. The first group we can deal with are known as integers. And the integers are the numbers from negative infinity to positive infinity, including 0, but not including decimals. So these are numbers like -4, -3, -2, -1, 0, 1, 2, 3, and so on and so forth. So all the way to positive infinity this way, and then all the way to negative infinity this way. All right, so these are our integers. Then we also have our whole numbers, which is what we've mainly been dealing with in pre-algebra up to this point. These are whole numbers, and the whole numbers are inclusive of 0, and they count to positive infinity. So no negative numbers, right? Because at this point, we haven't really dealt with negative numbers in pre-algebra. So this is what we've been dealing with. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to positive infinity, right? 157, 372, 5,025, right? These are all whole numbers. And finally, the last subcategory of rational numbers are natural numbers. And the natural numbers are essentially the same as the whole numbers, except for they do not include 0. So natural numbers start with 1 and they go to positive infinity. So they go on forever and ever and ever. All right. So these are all subcategories of rational numbers. Again, what makes these numbers rational is I can create each of these numbers as fractions. I can create them as the ratio of two integers. So for example, if I wanted to create the integer, or let's not deal with integers yet since we haven't dealt with it. Let's say I wanted to create the whole number 50. I can represent 50 as the ratio of two whole numbers, right? I can represent 50 as 50 over 1. I can also include in rational numbers repeating decimals. So decimals such as 0.3 repeating, so 0.3333, and then we can represent that as having a 0.3 with a bar over it. This means that 3 repeats indefinitely, forever. So a number like this, even though it's repeating, or excuse me, even though it's non-terminating, so similar to the irrational numbers is non-terminating, it goes on forever, it's non-terminating, but this one is repeating. It has a pattern. Every decimal is 3. So I can represent this as a ratio of 1 to 3. So if you do 1 divided by 3, you'll get this repeating decimal. So repeating decimals or non-terminating decimals that repeat, they have a pattern, are rational numbers because we can express them as a ratio of two integers, right? We can express them as a fraction. Other repeating decimals. So for example, let's say I have 0.4 repeating, which I can represent like this, 0.4 repeating. Generally, the repeating decimals are related to denominators of 9. So 4 repeating, 0.444444 is 4 ninths. And we can see that same thing in that 0.3 repeating is 3 ninths, which we simplify to 1/3. So 0.4 repeating is equal to 4 ninths. And then even random pattern decimals. So let's say I have 0.828282, right? So here again, another patterned decimal. This is a rational number because this is going to be equal to 82/99. Okay, so denominators with 999, 999 are related to our repeating decimals in this way. These are our rational numbers, and this is what we are basically going to be dealing with. So as we start talking about decimals, keep in mind that a decimal is a rational number. All right, decimal is a rational number unless it is a non-repeating, non-ending decimal, such as these examples here.